Okay, I think we are live now. So, good morning, everyone, and welcome to the last technical session of the series of technical sessions that we have been having. Um, this technical session is brought to you by one of the teams of eYRC, which is called Hologlyph Bots. Um, Before we begin with my monologue, I just want to know who is there in the audience right now. Even the people on YouTube can enter in the chat stuff like raise hands or emojis and stuff if it's uh, if it's valid for the question that I'm asking. So the first thing I was curious about is how many of you are listening here? Just to make sure that we need to get a zero of how many people are raising hands. So everyone who's listening, raise your hands or mention something in the chat, listening, or you can put an emoji in the chat. So everyone who is listening, raise your hands. And I should see ideally a decent percentage. I think the raised hand stays raised till you lower it. So keep it raised, don't lower it. Okay, okay, it's still 50% of the WebEx audience, and on YouTube, not so many. One person has. Okay, there's a lag between what I say here and that goes on YouTube, so that we can't help. Cool. So I think I see 50% of the audience has raised their hands. What about the rest? You guys not comfortable with WebEx? Is that the reason? I wonder. But I'm going to use this 50% as the datum now. That is my zero. Only 50% are going to respond to my questions, I think. So my next question is, how many of you know eYRC? So I guess all the people who have raised their hands can keep it raised if they know what is eYRC, if they have heard of it and they're taking part in it. Okay, first of all, if you have just heard about it, okay, everyone's hands still stays up, I guess, because you are here in the session. I'm expecting you to know about eYRC. How many of you registering for the event? Uh, Okay, so all the people who are raised their hands also registered for the event. That's good. Now for the final question, how many of you are planning to give hologlyph bots as their preference over here? I think you'll be soon. If you have registered, you would have had the form shared with you, where you can uh, give your preference of the theme of your choice. So how many of you out of the 50% who have their hands raised are planning to give hologlyph bots as their preference? You guys know the six themes, I'm presuming. If you know eYRC, you might have seen the six themes. There is drone and there's a lot of other things. Uh, so out of those six, how many of you planning to go for hologlyph bots? Okay, so I think a quarter of the audience here. So that's good. If you are planning to take part in hologlyph, this will be a great jump start. In fact, this is, I think, content from task 2. This is the stuff that we'll discuss very later on in the theme in part of stage 1. So if you know how eYRC works, it's a 6 month long competition, right? It starts now in September and it ends sometime in March, April. So what do we do for 6 months? I think people who have their hands raised already know how eYRC works. But if those who are just listening and sitting and are not aware, you can lower your hands now. Thanks. Although it doesn't take any effort here, you could just lower it anyway. Uh, so eYRC runs for 6 months. You have 3 months of stage 1 and 3 months of stage 2, right? In stage 1, you're usually working with simulators. Uh, and if you do well in stage 1 and selected for stage 2, then we ship hardware to those teams and then you get to work on hardware. So in hologlyph bot specifically, it's designed, and in fact in most themes, is designed in such a way that stage 1 is almost exactly replica of stage 2. The only difference is you're moving from simulator to hardware. So you're learning a lot during stage 1, and all of that gets transferred to hardware in stage 2. Of course, hardware costs, you need to buy hardware versus simulator. We use all open source simulators, ROS, Gazebo, and all of that, which you don't need to buy. So, of course, in stage 1, everyone is welcome. And in stage 2, we'll have to look at the dedicated ones and select the ones who will be shipping the hardware to. I guess that would make sense. So that's the story of eYRC. And of course, at the end of all of that, there is a grand finale that happens at IIT Bombay, where all the top few teams, top 10 at max, top six to top 6 to 10 teams come to IIT Bombay and present their bots in front of professors and whatnot. Again, in that, if you're selected, you get an opportunity to take part in the eYantra summer internship program, which runs for 6 weeks during the summer after the competition. So this is the story of eYRC and eYSIP. Just for those who are not aware of it, I guess half of you already knew all this, but still sharing it anyway. So yeah, I was saying that stage 1 and stage 2, right? Stage 1 is the simulator phase for 3 months, and then stage 2 is the hardware phase in the after December, November, December. So in the stage 1, the task, there are tasks 0, 1, and 2. Task 0 is usually just setup. Task 1 is a step higher where you learn the basics. And then step 2 is a step higher, of course, where you have almost learned everything that is needed to do something in hardware, except, of course, there's a big jump from switching from simulator to hardware. But in task 2, there is something that we discuss, which is kinematics. And that is the main content of today's session. We'll be discussing kinematics and of course kinematics of what robot? It will be the um, holonomic drive robot. So what is a holonomic drive robot, and all of that also will be today's agenda, which will probably run for an hour or so, at least my monologue. Only 16 I have to give presentation. Yeah, so that is the finale, and usually it is only, unfortunately, there is a very clear demarcation between the top 6 to 10 teams and the teams that are following them. So it's very easy for us to select sometimes the top 6 teams. I hope this time you guys are enthusiastic about the holograph bots and you'll give us a tough time selecting the top 6 teams. Then we could probably consider even a bigger number. So it is usually the top 6 to 10 teams that are actually impressive enough to be presented to professors of IIT Bombay and guests from industry and whatnot. Um, so yes, to answer that was the answering Yash Raj's question in the chat. So if you have any questions, you can keep putting it in the chat and we'll answer it one by one whenever we get the chance. Um, Cool. So I think I've set up the picture here for today's session and this picture for the next 6 months. Um, and also I should mention today is the deadline for registration. So you should register if you have not already registered. It will be an exciting journey, of course. I myself was a participant in 2016 when I was in my second year. And right now I'm working for the team as well and I'm doing masters and whatnot. So I should, I guess, introduce the team behind this particular theme. This today's session is brought to you by Hologlyph Bots, as I said, right? So that particular theme, there are developers who develop that theme, who manage that theme, and then all your queries are answered by this team when you are in the discussion forum very soon, if you have registered to that team. So the team here is Bhargav and Sri Venkateshwar, who you can see with the cameras turned on. And there is Abhishek as well, who has not turned on his camera. He might turn it on sometime soon. So there are 4 of us in this team, and me, myself, Arjun, are the 4 theme developers for this theme. So I think all introductions are done, and you'll be seeing these names very often in the discussion forum. They'll be the ones with the technical expertise and all of that required to answer your questions. So yes, what else? I think we can start with the session. You guys have anything to ask before we start with the technical session? I'll give a couple of minutes for the YouTube people as well to respond. I'm not sure if I got that question completely, but my understanding is you're concerned about how the evaluation and selection happens, right? So actually, the good news is in stage one, there is no elimination. Yeah, so we don't do elimination throughout the stage one, although we do give feedback and we tell you if you have finished the task successfully or not. It will be a success or fail in the particular task, but not necessarily meaning elimination. The elimination happens only when we choose for stage two, from stage one to stage two. Uh, and usually, as long as you have followed the story along with us and you have implemented, so that's Abhishek who has just joined us, the fourth member of the team, since we have introduced everyone. Okay, so I was saying elimination doesn't happen till stage one ends, but based on your performance in stage one, we have to eliminate and select the top n number of teams to whom we will be sending hardware. Because hardware costs money, you can't just send it to everyone and anyone interested. We'll have to see if you are willing to put the effort at least. Most of the time, everything that is needed, at least the guidance that is needed is given in the documentation that we provide. Uh, a lot of guidance is given in the documentation. Of course, you'll have to work beyond that as well because it's a competition as well. You'll be given the stepping stones to reach the final step, but the final step will be left for you to take based on all the things that you have learned while coming to that point. Um, oh, okay. Okay, if there is any audio issue, then I'll turn off my video. For now, I'll leave it on, I guess. Anyway, I'll be ending the monologue now. So, yeah, the elimination is usually just to eliminate people who have not worked at all. Usually, most people who have satisfied, like completed the tasks, usually make it to stage two. It's very rare that someone who has completed the tasks successfully is not going to stage two. So, yeah, I think you just need to focus on completing the tasks and you will make it to stage two, is what I'm saying. Uh, oh, that's fine. Yeah, that's absolutely fine. It's good that you're interacting with us. It's nice to see interaction. So I would encourage everyone to interact in the chat as well. So cool. I was just responding to Yashraj's comment. Okay. So shall we begin then? I think we can begin. I don't think I have anything else to say. If you have anything to ask about eYRC or eYSIP or anything like that, you can ask us. Uh, yeah, let's begin then. I'll share the entire presentation today will be just a screen share. So I'll just share my screen now and I'll turn off my video since I'll be keeping it horizontal. Mm, okay, I think you should be seeing my screen now. Okay, we'll start then. So the topic for today was, as I mentioned earlier, holonomic drive robots, a discussion on kinematics. There are two things that are of interest here. What is a holonomic drive robot itself, first of all? That's a quite a new word for us, most of us. And kinematics is another interesting word that you might have heard of in classes. Speaking of which, another poll that I forgot to take, how many of you are from mechanical and related fields of discipline, mechanical or even, yeah, mechanical, first of all, uh, and similar fields like civil or and basically non-electronics and computer science. Let me put it that way. Anyone, how many of you are not from electronics, electrical, or computer science? Okay, I see a few responses, mechanical, civil. Cool. Okay, so there are a few mechies here and a few civil people as well. How about electronics and electrical and related fields, telecommunication and things like that? Probably even instrumentation and controls or something like that. All of those people raise your hands. Oh, a lot of mechies here. I'm still seeing a lot of mech responses. Uh, okay, what is hmm. ENC, a few electronics and communication people are raising their hands now. Three, four, a few more coming up. Yeah, by the way, if you're raising your hands instead, you can just put it in the chat because it's easier to see it in the chat, which department you guys are from. And how about computer science, programming and computer related fields, IT and computer science? I see no responses as of now for computer science or okay. A lot of proud Meckies here. That's good. Okay, cool. So I think I know my audience, right? Oh, interdisciplinary fields like mechatronics as well, if any. And also you can mention any other departments that I have not mentioned. Maybe you're from sciences or arts and humanities and whatnot. Okay, I think I've gotten a decent understanding of the audience here. So the word robot itself, to me, I have a definition that I ask. I ask everyone this question. What is, uh, okay, people are asking annotation requests. Uh, anyway, so what is a robot itself is an interesting question, right? There are many definitions, but the definition that I like is the sense, think, act paradigm. Am I spelling it right? It's a sense, think, act paradigm. I would request people to not ask for annotation requests. Of course, I'm not going to allow that. So, uh, yeah, okay. Mm, so, the way I like to think of a robot is it has at least these three parts, the sense part, it has a think part, also sometimes called plan part, and the act part. So it should be able to have, I think most robots should have some sensors on board, some actuators on board, and some kind of microcontroller or microprocessor or FPGA or what else? Yeah, something like that on board to do the thinking. Um, I guess that everyone would agree on that. It's very difficult to have an interactive session while we are online, so I'm just going to keep it very monologuous in nature, but I hope you guys are on board. And if you have any questions, please do interrupt in the chat. And if we feel the need for it, we could even allow you to unmute your mic. But yeah. Cool. So yeah, sense, think, and act. That's why I asked the question in these three ways. I asked how many of you are from electronics. Actually, this is all these three have a fusion of three things. The think is somewhat very computer sciencey. The act and sense is a fusion of mech and electronics, and even some things like controls. Um, which is sometimes a separate discipline. My discipline is right now masters in systems and control. So yeah, sense and think is a mixture of these two, three things. Mechatronics is also, you could say. And think is usually a computer science. So there is one person at least from computer science I noticed now. Cool. So that's why I just got curious. Anyway, fine. So today our discussion is somewhat on the act side of things. We are going to discuss the act side of things. Of course, you could distribute it. There is a bit of thinking as well, not our thinking. The robot's thinking will depend on how the robot acts. So let's say we are somewhere in this region, the thinking and acting region. So when it comes to that, for sure you need a mechie kind of knowledge. Uh, you need not be a mechanical engineer. I can do programming and I'm not a computer science student. Similarly, my colleagues here are also not mechies, but they're doing hardware on, they're building holonomic drive robots and understanding the kinematics and all that. So, I mean, the world is, of course, a very interdisciplinary progressing towards all interdisciplinary natured projects. So we'll need to learn to be interdisciplinary. Therefore, this session is welcome to everyone in the chat, whether you're a mechie, electronics, or computer science. It's good to know all of the things that we are discussing today. There is a discipline that is not usually given as much emphasis as it should be. Uh, if you are especially getting into the field of robotics, which is a sciencey type of department. I think most colleges have a mathematics department separately, and most of you have some electives in the field of mathematics. But you probably, I mean, the amount of importance you give to this varies a lot. I myself realize the importance of linear algebra, multivariable calculus, um, right, MVC, or complex analysis. These are all very deep subjects, of course. You don't need to dive so deep into all of this, but you do need all of this in your engineering applications. So today there is going to be a lot of mathematics as well, especially from the Department of Linear Algebra. Will not get into multivariable calculus, and calculus won't come here today, at least. So for those who are afraid of calculus, good news, but I would encourage you not to be afraid of calculus as soon as possible. So cool. So we'll be bringing up linear algebra today. And as I said, we'll be discussing kinematics, which is usually a subject that is brought up in mechanical syllabus. Probably they have robotics and whatnot. And there they understand something called forward and inverse kinematics. We'll look at that for a ground vehicle today. Usually they do it in a robotic arm context, just a serial coupling of links, a serial linkage kind of setup. But today we are not doing that. We are doing it on a ground vehicle. On a plane, there is a vehicle kind of setup. Should I? So vehicle. In 3D, it's difficult to show a vehicle. Anyway, so that's the topic, of course, since we are talking about ground vehicles. Cool. I think enough introduction. As I said, the team who is introducing this is Hologlyph, and that is because the theme of Hologlyph bots, task 2 of stage 1 is basically going to use heavily all the concepts that we are discussing today. So you'll not need it immediately as soon as you register. Task 1, you will not need this. You'll be learning something about controls in task 1, which we'll not discuss today. But the understanding of what we are discussing today will be essential for doing that as well. There's not a prerequisite. All of this will be covered again in the theme, so you don't need to worry too much about it. Cool. So I'll move on then. Uh, Should I stop for questions? Any questions? Should I wait for a minute? Any questions? I'll wait for a minute, half a minute. Okay, I see some YouTube people as well entering electrical and electronics as their discipline, so that's good. Okay. I guess there are no questions about what our agenda is. So far, I've just been discussing high-level picture and probably even connecting what you are learning here to your coursework. Uh, we don't realize the importance of coursework when we are as a hobbyist, and as a coursework person, you don't realize the importance as a hobbyist. So the relationship between these two things is quite an amazing thing. And as a complete engineer, you need to be both of them, is what I believe. So today we are looking at it as hardware, people who will work on hardware and things like that. But the things that we learn in course is what we should be using while we do all this to become a complete engineer, in my opinion. So anyway, enough preaching. Let's go on to what is a holonomic drive robot. Uh, well, I Googled it. I asked Google what is holonomic. I guess nowadays you should ask what ChatGPT. But anyway, I asked Google, and Google said holonomic refers to the relationship between controllable and total degrees of freedom of a robot. Controllable and total degrees of freedom of a robot. If the controllable degrees of freedom is equal to the total degrees of freedom, then the robot is said to be holonomic. That is the definition I found on Google. So a lot of words came up there, controllable and total degrees of freedom. Uh, so now we'll look at what is degrees of freedom, which is a familiar concept for the Mechis, I hope. But sometimes it's not, because I've asked people in the interviews and they stumble even at these basic things. So today again we'll discuss what is the degrees of freedom of a rigid body, of a rigid body to be more specific. Rigid bodies degrees of freedom. So here I have two pictures shown on the left and right. On the left I have the three-dimensional space. A very familiar space for us. So I'm starting there. And I have a cube kept in the three-dimensional space. Uh, so can you tell me how many degrees of freedom does this have? Just based on intuition. It's a very intuitive question. So if you can you answer how many degrees of freedom does this cube have? How much freedom does it have? Is basically what I'm asking. Uh, uh, to help you out, it's a number between 1 to 10 or 0 to 10. So can you think of what number would make a lot of sense here in this context? How many independent directions can I explore? Is another way to put that question. 6. Okay, so good to see. I hope the Mechie should answer some answers should be coming from the Mechies. I would forgive the electronics and computer science students to not answer this question, but the people from mechanical must answer this question. And in fact, I encourage the others as well. I would expect a different answer. Yes, that's the answer that I'm expecting. Viraj entered 3. Intuitively, when I ask, I think the answer would be 3, right? What are the 3? Can someone tell me in the chat? I think most would agree, even if I don't wait for the answer, that the 3 degrees are I can move in the x-axis, I can move in the y-axis, and I can move in the z-axis. These are 3 different unique directions that I can explore, right? So 3 is the answer, or is it? Is it 3? Why did some of the people answer 6? Can you think of what is left? Is there something more? It's clearly more than 3 or less equal to 3. A lot of people answered 3. So 3 degrees of freedom, but is it? Are we missing another kind of degree of freedom that we are not considering? What else can this block do? I have a block in space. Uh, I don't think I need to show with the camera, but you could visualize. I would encourage all of you to have an image in the head of a block or an actual block in front of you. Right. So Vijay answered the question directly to the point, which is three translations we discovered, but we didn't discuss the three rotations. I could rotate in this axis, and I could rotate in this axis, and I could rotate in this axis. So the questions I'm asking are pretty simple. Don't hesitate to answer. Feel confident. I myself am a victim of that. Even if I feel quite confidently, I'll still not say it because I am never having enough confidence to answer the question that a prof asks. But I would encourage you to do that. So 3 degrees of translation and 3 degrees of freedom in the rotation. So if I give you an object in space using 6 numbers, which I can stack in vector, you should be able to tell me the configuration of this body. So I'll give you 6 numbers: x, y, z, alpha, beta, gamma. Using these 6 numbers, usually they might have some units also, meters and radians, right? These are all in meters and these are all in radians in this case. So if I give you these 6 numbers, you can tell me exactly where the object is. This is an important point to understand, that there are 6 numbers that I need to uniquely identify where the object is. Very soon that object will become a robot. If it was a flying robot, I would need 6 variables to uniquely define its position in the 3-dimensional space. But now let's talk about this ground object on the ground. It is stuck to the ground. It's not allowed to, this surface that I'm highlighting now is stuck to this surface. That is my constraint. With that constraint, how many degrees of freedom do I have? 2 degrees of freedom, right? That would be the expected answer. But is it two? The same question. Of course, the two that makes sense is I can translate in the x, and I'll probably change the color a little bit. I can translate in the x and I can translate in the y. 2 degrees of freedom. Anything else? Anything else? Is it just two? Four? Oh, what are the four? Maybe Rahul, you could explain what the four is in the chat. Uh, I can see X is possible. I can see Y is possible intuitively. What else is possible? Is there a degree of freedom that we have not explored or more? Anyone? It's quite a intuitive answer. You can just think about, just put a object on the ground and move it around and see what can you do with that. I want an answer from the audience. I won't give this answer away for free. It's too easy a question to be answered by me. You will have to answer this question. Ah, okay. So I see someone. Right. I see the answer on YouTube. WebEx people have not answered yet. Uh, I see the correct answer on YouTube. Yes. WebEx, anyone wants to answer? No? How come? There are so many Mekis. I expect better intuition from you guys. Exactly. Finally. So, okay. Is it the same guy? No, it's different. So you can rotate in the Z axis, right? Uh, You can rotate in the z-axis. Is the z-axis. You can't move along the z-axis, but you can rotate this body along the z-axis. That is possible without leaving the surface. Right, so it has only three. You can't translate in the z-axis. This is not possible, but you can rotate about the z-axis. You can't rotate about the x-axis either, because then the surface will have to leave the surface. This surface contact will be gone. You can't do that, of course, in the y-axis as well. But you can do that in the z-axis without leaving the surface. So how many variables do I need to uniquely define the position of this object? I need an x and a y and a theta. Three variables, right? So given these three variables, I can uniquely tell position of this object in two-dimensional plane. Okay. For example, I can define it like this. I can say it is not exactly tilted, but I'll force it to be a little tilted. Uh, Theta for the amount of tilt and x and y is the exact position of this corner. So x and y is the position of this corner of this cube, and theta is the angle between this edge and the zero, which is basically the x-axis. I just translate the x-axis and the angle. Uh, so yeah, these three variables, corner position and this theta, is enough to explain the exact orientation of the entire rigid body. It is a rigid body is the point here. So if I just tell you the position of this edge and this corner, you can tell me the rest of the body's orientation and position, right? So that is how we do. I mean, the problem of localization in robotics, localization is another keyword that we are not discussing today. When I said sense, think, act, that is from here, the sense part. But the problem of localization is exactly to figure out what is x, what is y, and what is theta at any given time. If you can tell me what is x, y, and theta, then you have solved the problem of where is my robot. So for those who are new in the field of robotics, this word should now make sense to you. Whenever someone says localization, this is kind of what the problem is. What is the x, y, and theta? This is like the systematic way to define the problem of localization, I guess. Of course, you can get into greater detail, but yeah. With respect to a frame, there is a frame that is stationary. That I should, of course, mention. There's the global frame. The global frame. I'm representing it with curly brackets. The global frame, G, and there's a local frame, which is defined by this edge, and I'll call it B, bot. Instead of a box, if I had a bot there, then that bot has a frame and there's a global frame. The relationship between these two frames is what localization answers. And it's important to understand that the position of the robot, pose of the robot is another word. Pose. Pose is what? Position and orientation. Position and orientation of this robot is defined by something called the pose of the robot, and that's what is defined here. The pose of the robot is defined using x, y, and theta. Cool. So once we have that clear, now comes more interesting problems. Anyway, there is another word, fancier word, configuration, which also means that only. I can define the configuration of the robot using x, y, and theta. There's something called a configuration space, which in some cases would be a vector space, or at least we try to have a vector space. And this is why you need to study linear algebra in colleges or wherever you study linear algebra. Because linear algebra is trying to understand a vector space and its behaviors and how it transforms and all of that. Uh, So yeah, cool. Now let's talk about some constraints. Any questions so far? I don't think so. I think it was quite easy, right? I hope it was quite easy. And we just learned a bunch of vocabulary, that's all. So vocabulary and some basics is all we did so far. So let's move on to constraints. Of course, robots in the real world have constraints. It's not like if I had a surface and just a block and that block is moving freely to do whatever. That is not what a robot is, right? If a robot has two wheels, you can't slide the robot in this direction. Intuitively, it makes sense. I mean, you would have realized that by now. Or if you had a car that has a Ackerman steering, can you do parallel parking by just simply pushing the car this direction? You can't. It has some kind of constraints that doesn't allow it to simply move in this direction. You can't apply a force in this direction. You can do something like that and come back and park. This is a very interesting point that I'll bring up again in a couple of minutes. But these are what we call constraints. It stops the robot from doing a few things. So I could define a constraint like this. There's a, if for the rigid body itself, let's come back to rigid bodies. I have a ball or something like a ball, let's say. It is sitting on a groove. This is a plane. Uh, and in that plane, I have made a groove. The ball is sitting inside that groove, and of course, because of the design, the ball cannot come here. It cannot leave this groove, right? It's a very steep groove. No matter how much force you apply, it's not going to jump out of this groove. It's going to slide along this groove only. So this, if it was a robot as well, you could think of a robot, for example, if it was a railway line and you have a railway like uh, bot. If this is a railway track and this is a train, which is cartoon train. This cartoon train won't get out of this rail, right? It cannot, uh, the train can never reach this position. This X, Y, and theta, it can never achieve. No matter what controls you do, you'll not be able to achieve this. You can, of course, achieve this particular X, Y, and theta. These kind of constraints are what are called holonomic constraints, where you're not allowed to explore the entire x, y, and theta. This particular x, y, and theta, you're not allowed to explore. This particular x, y, and theta, I can represent x, y, and theta with a point and an arrow, right? That's what I'm doing here. So the point represents the x, y, and the angle with respect to whatever global frame you have decided is the theta. So this particular x, y, theta is impossible. This particular x, y, theta is impossible. You just cannot do it because of the way the system is decided. These kind of constraints on the system is what we call holonomic constraints. Holonomic constraints. The word holonomic drive, do not mix it up with this. It is actually kind of ulta. Holonomic drive does not have holonomic constraints is what it means, funnily enough. Uh, in fact, it doesn't even have non-holonomic constraints. It might have holonomic constraints if you put a cage around which you can't leave or something like that. But this is the adjective for constraint type. Cool. Non-holonomic constraint is what then? Does anyone have a guess? It is a type of constraint. There's some constraint on the system, but what? What kind of constraint? Well, of course, it's a little complex question. I'll answer this right away because answering that in the chat would be a difficult job. So this is a rolling coin. Uh, this is a rolling coin. I hope the visualization is clear, which is pointing in that direction, and it can roll like that. This rolling coin is not allowed to slide like that. The coin is not allowed to slide like that. This is not allowed. Uh, the rule that it cannot slide like this is a constraint, right? It is some kind of constraint. It cannot slide like this. There's a rule that is imposed on this rolling coin. So this is a constraint, but can this rolling coin achieve any particular x and y that I wanted to achieve? This particular position, can it achieve? Yes or no in the chat? Can the rolling coin eventually somehow, it cannot slide like this. It is not allowed to come here directly. But can it come here somehow using some other means? No? Uh, what does YouTube think? The rule says that the sliding coin is not allowed to slide in this direction. But I want it to eventually come somewhere here, where in this direction. Uh, this is new position and this is old position. Is it possible? Yes or no? No, no. Two people say no. Of course, what is allowed is you can roll the coin. You can roll the coin in this direction. You can also rotate the coin in this direction about this axis. There is a vertical axis, right, on which the coin is. And you're allowed to rotate in this axis. Eh, you can roll the coin in this axis, which is the rolling action. Usually, however, coins roll. And you can also rotate the cone in the perpendicular axis, perpendicular to the ground. Now, can you achieve this particular position and orientation that I wanted to achieve eventually? Yes, so in YouTube they say yes. And okay, Kishore also says yes. Of course it is possible. Uh, how is it possible? You just rotate the coin, face it this way, and then roll this way, and then rotate it back this way. Just like a coin. You take a coin and do it. It's possible, right? Without slipping in this direction, you'll be able to go in this direction by just rotating the entire pot. So what kind of constraint is this? It is allowed to go anywhere. I can go achieve any particular position x, y, and theta. Any x, y, and theta this coin can achieve. But it cannot achieve freely however it wants. It will have to rotate and slide and all of that. So a car, for example, can do parallel parking. It's not impossible, but it cannot do directly. You can't just go like that. You'll have to do some more complicated maneuvers. So that is what is called a non-holonomic constraint. So constraints are like that of two types. I hope that's clear. This is actually probably an unnecessarily complicated topic introduced too early on. But it's intuitive enough, so I introduced it. I might as well introduce it. Because we may not need this. I'm just describing these two kinds of constraints, that they have a name also. The constraints make sense, so I just give it a name. I mean, name was given, I'm telling you the name, that's all. So here are two robots that I have. One of them is a non-holonomic drive robot, and the other one is a holonomic drive robot. Here it's somewhat difficult to relate it with this non-holonomic constraint and holonomic constraint. But what this robot has is a non-holonomic constraint because it cannot slide in this direction. It cannot slide in this direction. It can go forward in this direction, and it can also pivot in the vertical axis. It can also achieve this motion, but it cannot slide in this motion. So this is almost equivalent to the rolling coin that we discussed earlier. In many ways, this is equal to the rolling coin. It's also sometimes called the unicycle model. We will discuss this also very soon. Because a unicycle also is this, no? It is just one wheel with a pedal attached and a seat over here. So this is a unicycle or a rolling coin. While on the right is a very interesting looking robot with very fancy looking wheels, which are known as mechanism wheels. Mm. And that is the kind of robot that we will be using in our theme. Not exactly this. Here we are using mechanism wheels. In our theme, we will use what is known as Omni-wheels. So Omni-wheels can be made in 3-wheel configuration as well. This is a 4-wheel configuration. You can see there are 4 wheels with fancy looking rollers kept at a very absurd angle of 45 degrees. Uh, there are other rollers that you will see not in this presentation, but if you search Google search Omni-wheel, you will see a wheel with rollers in the perpendicular direction. Instead of rolling in 45 degrees, they'll roll in this axis, something like that. Cool. This allows for what? It can do both translation in X, it can translate in Y, it can translate in omega. All 3 degrees of freedom that was possible for this, for a body on a plane, we discussed here, right? This body in the plane case. It had 3 degrees of freedom. It could translate in X, it could translate in Y, and it could rotate in Z. In other words, I could also write Vx, Vy, and omega. It can have a linear velocity in X and Y, and an angular velocity in the Z axis. If you want, you can put omega Z. This is another way to just say that it has 3 degrees of freedom, right? It can translate in X and Y linearly, and it can rotate in vertical axis with angular velocity omega Z. So this can achieve all of the 3. It can uh, it can achieve Vy, it can achieve Vx, and in the perpendicular direction, it can achieve omega Z. How does it do that is what we'll discuss next, and that is the topic of kinematics. I think we are on track. About half an hour, I should be completing kinematics, and then we'll have a quiz and wrap it up. So make sure you pay attention to all the things I'm saying because we will be testing you for the certificate and stuff. So, okay, any questions so far? I see. I've not seen the car yet, but yeah, there are cars that have Omni wheels on them. Quite interesting. Uh, cool. So I guess there are no questions, and therefore I shall move on. Right. If there are any questions on YouTube also, you can ask. I'm checking. We are checking both YouTube and WebEx questions, so feel free to ask on YouTube as well. But before we get to this hologlyph bot theme, let's look at something more basic. I think this is something that we are more familiar with, right? Just put 2 wheels on a motor and you have a robot. Quite simple. So let's discuss that first. There's a fancy name for that, of course. It's called differential drive because you have 2 wheels that can be independently controlled in 2 different directions. And we'll discuss that particular bodies, forward and inverse kinematics. So, kinematics, first of all, what is kinematics? You might have also heard of something called dynamics. Mm, you might have also heard of something called kinetics. And what I'm talking about today is kinematics. What are these words? So, uh, there is mass, there are forces, there are torques that are required to actually make this bot move, right? Based on all of that Newton stuff and F equal to ma and the angular corresponding to that inertia matrix and m equal to a omega dot, whatever that is called alpha. Anyway, so you have all the linear and angular forces equations, right? F equal to ma kind of equations. All of that comes in dynamics. What we are not interested in kinematics is we don't care about the mass of the bot. We don't care about how much force is required to actually push this wheel and achieve a certain velocity. We don't care about the torque required for this motor. There are motors attached to this, right? We don't care about that. We don't care about inertia matrix that describes the weight distribution and how it's distributed and so on. Inertia matrix we don't care about. All of that is not needed. Then what do we care about? We care about geometry of the bot and we care about velocities of the bot. It's a relationship between velocities. Very simple thing. So even I could teach this to a school kid if I wanted to, because they've learned geometry and they've learned something about velocities. They know what is a linear and angular velocity. So therefore, we'll discuss kinematics today. Dynamics is required for simulations and whatnot. Of course, it's a very important topic, but we'll not get into that today. Uh, so today, what is our picture of this differential drive robot? I have a differential drive robot here, a generic one that has a chassis. Uh, It has a caster wheel, if you know what that is. It has motors. It has a wheel of certain width and radius and all that. And it has a certain shape, whatever complex shape it has. For us today, it is equal to this. This picture over here and this picture over here are the same for us. They are the same. Uh, the only numbers I care about is radius of the wheel and the length of the axis. This is the only thing I need to know. I don't need to know where the caster wheel is. I don't need to know where the center of mass is for discussing kinematics. Cool. So from now on, our differential drive robot is just that. This is my differential drive robot, completely defined. Okay, we shall see why. Because now the question that I'm going to ask is, what kind of motions can I achieve with this particular bot? Um, How do I start? So I'll actually simplify this further. There's a layer beyond this as well. I could in fact remove even the R and just call it that. How do I do that? Actually, the wheel has a angular velocity uh, phi 1, let's call it phi L, 5R, and this has a 5L, yeah, phi L. Then there is the radius. So R into phi R, the radius of the wheel, is basically VR, is what I'm going to call it, which is the linear velocity represented here of this wheel at that instant. Uh, and this particular wheel will have VL, and VL is just basically R times phi R, uh, phi L, sorry. What is phi L? It is radians per second of the wheel. This is just meters or mm or centimeters, whatever. This is in mm per second or meter per second or whatever, right? So this picture I am going to neglect and I'm going to further simplify this model to just 2 points separated by a distance of L. So even the radius of the wheel won't be of concern for me, because now what I'm going to work with is left wheel velocity and right wheel velocity. Cool. So the velocity of this robot, what can it achieve? I can achieve any particular left wheel and right wheel velocity by giving the command to this motor. So eventually, once I have decided this, I will calculate whatever RPM is needed and give it to this motor, respectively for left and right. So this is my differential drive robot now. A lot of people saying hi right now in the chat. Uh, cool. Hi, hi. Welcome. Anyway, so continuing on, uh, this is my robot, and now I'm asking the question of, uh, let me draw that robot here. I can achieve forward and reverse velocities. My question is, how will the robot move if I keep a constant velocity? Let's say this velocity. I give it this velocity. And the magnitude of this arrow is the magnitude of the velocity. Given that, can you tell me how will this robot move? Will it go left, right, straight? What kind of trajectory will it follow? It'll go right, okay, it'll go right. But how exactly will it go right? More precise answer can you give? What is the complete trajectory? I'm not going to change the velocity. If I observe this for, exactly. So it's going to be a circle, right? I could have asked one of you to come to the board and draw this, because now the next question is, what is the circle that it will trace? I can geometrically show you exactly the dimensions of the circle, exactly the shape that circle will be. It will be a circle. It could be a circle like that. It could be a circle like that. So many circles exist, right, of different radiuses and radii, and so the circle is going to be like this, roughly. Yeah, something like that. How did I do that? The center of the circle is always going to be on this line for a differential drive robot. And in fact, precisely where it will be the intersection of this line and that line. And that is the circle it will trace. Uh, Precisely that, as long as I make sure that these arrow sizes make sense. In fact, as long as the scale of the arrow is the proportion, the scale that the ratio of VR and VL is exactly as it will be somewhat like this. Maybe the diameter will change a little bit, be parallel. So yeah, it should represent the exact magnitude. So this will be the circle that it will trace. Uh, so if it is tracing a circle, would you remember how would you represent a body rotating on a string at the center if you're rotating like that? You had another way to represent it, right? We had omega over here, and it had a linear velocity v. Uh, this can achieve uh, uh, a particular omega and a linear velocity is what we are going to do now. So every robot we represent it like this. In fact, when we don't, eventually what we'll be doing is we'll be showing it like this. But practically, what is happening is it's kind of defining the radius of this circle, this omega. Uh, in fact, what exactly is the radius? Does anyone know? If I know r and omega, high school maths. Someone said irregular for when I was asking the question of what trajectory will it trace. That is true in real world, but in my kinematics world, it is ideal. So I know exactly the circle that it will trace. So R is just V by omega, right? Um and therefore, instead of writing V and omega, I could say V and R also equivalently. I could say V and omega also equivalently. I could, now this is the interesting point. I could equivalently, this is the key point, very important point. I could equivalently say VL, VR. There's a big difference. To get from here to here, it was quite easy, right? You just divide um, V by omega and you get R. So these two is a one-to-one relationship. for every V and omega, there is a unique V and R, bijective also called bijective mapping. This is also a bijective mapping as long as L is non-zero, to be very precise. Uh, just to be clear, the length, not left, the capital L I will use. The capital L is this. As long as the bot has some size, it is a bijective relationship between V and radius or V and omega. I prefer to talk about V and omega. So V and omega and VL and VR. And this particular mapping, the bijective, this is a map, bijective map. This particular mapping is what is kind of forward and inverse kinematics, depending on which arrow you're pointing towards, FK and IK. One direction is forward, other direction is inverse. The intuition behind forward and inverse for me would be if I have a chat. So which one is easier to work with for a human being? Here is a question. For a human being, which model would you prefer? These are so what did I say when I said it's a bijective map? You could completely ignore you as if you know this, you know this. If you know that, you know this. There is literally no new information. It's just a change of language. You just said the same sentence from English or Hindi or any other language for that matter. You just change the language is all. The sentence or the meaning of that sentence is the same. These two are literally the same thing. You just change the basis. So if you want the technical term for that, it is a change of basis. If a linear algebra term for that. And what is actually happening is a transformation. Some matrix defines that transformation. All of that is there, but anyway, we will define that matrix as well. So anyway, so is that clear? What is, yeah, I asked a question. As a human being, which one would you prefer? These are equivalent, right? I could describe the robot's motion using left wheel, right wheel velocities. I could describe the robot motion using bot's linear and angular velocity. Which of this is your, as a human being, which one would you prefer? And as a robot, which one would you prefer? As a human being, which one first? No answers? Okay, probably it's not so intuitive, but a human would prefer to work with V and omega. Uh, why? Because you just have to say how fast you want to go ahead and how fast do you want to turn. Are the two values have a meaning to it. How fast do you want to go straight and how fast do you want to turn? If you go V non-zero, V greater than 0, omega equal to 0, uh, then it's very immediately clear that the bot will go straight if the bot starts here. If I say V equal to 0 and omega equal to omega greater than 0, it's very immediately clear that this robot will spin on its own spot because it's not going to go straight at all. 0 linear velocity, full angular velocity, right? If I say V equal to 1, omega equal to 1, then you know it will make this circle. And if I say V equal to 1, omega equal to 2, and it started here, and the robot started here, and it implemented this circle. When you did V equal to 1, this case, or V equal to 1 and omega equal to 2, it will form this circle. Intuitively, it makes sense. So you know exactly what it will do given these two numbers, very intuitively. But if I give you left wheel and right wheel, you will have to eventually convert it to V and omega and then think in those terms. But what does the robot need? It needs VLVR. It is the world. The robot lives in, robot doesn't understand V and omega. This is the robot's world, and this is the human world. or the actually human, or more precisely control world. We like to implement control systems on this rather than this, because control systems is very difficult to implement in the motor level directly. It's easier to control V and omega, because we'll say go this fast in the forward direction and slowly turn in this direction. I don't want to say increase this one this much and then you decrease this one this much and then you adjust. That is too difficult to explain that, right? So that's why we need this mapping, and that's going from the human world to this one is inverse kinematics, and coming from here to here is forward kinematics. Cool. So then let's move on and take some. I just have a picture of the same thing, uh, and I also have the now mathematical definition of the same. Omega is the difference divided by L. So the more the difference, the greater the omega will be, which should make sense. If the difference in this is what? It's basically this. The more the difference is, the steeper the angle will be, right? Uh, if this wheel is that and this wheel is this angle is steep. If the difference is smaller, the angle is smaller. So this angle is basically representing omega in some sense, right? So yeah, that further can be made into a transformation described like this, a matrix operation. V and omega over here and VRVL over here. You take the inverse of that, you get this. This matrix is just the inverse of this matrix. Uh, I hope this intuition makes sense, first of all. V is just the average velocity. This is literally the formula for average. And this is literally the formula for difference. So difference gives you angular velocity and average gives you the linear velocity. Difference, of course, scaled difference, I should say, because this L exists here. And once you understand that, I'm just rephrasing it like this. This is also an exercise that you're very familiar with. You have written a bunch of equations and solved them in similar fashion. So yeah, this is what is kinematics. Does it make sense? Mm, we applied kinematics to a very different kind of system. In your coursework, you would have applied kinematics to serial linkages, right? A robotic arm, where you answer the question of where is this point? The x, y, theta is x, y, z, alpha, beta, gamma. Because if you have six links, 1, 2, 3, 4, 5, 6, then yeah, if you have arranged those links properly and joins properly, you should be able to control all six variables to some extent. Uh, so the question of what is this, and then actually what you have is theta 1, theta 2, theta 3, theta 4, and so on. You could change that question also to omega 1, omega 2, omega 3, omega 4, the angular velocity of each of these links, and Vx, Vy, omega, Vz, and some angular velocities respectively. This question is what we did here for the ground vehicle. Uh, I would urge you to go and think about this further if it is not already clear. But this should be quite simple. This is a simpler system to work with, so it should be easier to understand. And of course, as I said, it's a change of basis. So if you want to think of it from a mathematician's perspective, then all of these terms is what also gets introduced. Okay, I think it's high time the hologlyph theme comes into picture, and that is basically the holonomic drive robot. Hmm. I think I will give away the answers a little more easily now because anyway, if you are more interested in this, I would urge you to register for the competition and put hologlyph theme as your preference. Then you might end up in the theme, and we'll explain all of this further. But okay, there is one question. So, okay, I'll give you the answers now, and I'll give you the final. I'll give you the my experience directly. I'll feed it to you. But the actual way to learn it is you do it and you experience it. So for now, I'm not going to ask questions. I'm just going to tell you what it is, and then you can think about it. So the configuration that we have here is a three Omni-wheel robot, which has three wheels kept at 120 degrees from each other. The axles are kept 120 degrees away, so quite symmetric. What these wheels are they allow complete non-slip condition in this direction and full slipping in this direction. So these have rollers that allow if I push this in this direction, it will just go. So can you guess what would happen if I rotate these two wheels in these two directions? Similar as those regular wheels, I represented the arrow with, I'll name them now, 1, 2, and 3, let's say. So V2 and V3 are these vectors. Then what is how do I represent the bot's velocity? This time it will be Vx, Vy, and omega. Last time we had V and omega, right, in differential drive. Now we'll have Vx, Vy, and omega. What is Vx, Vy, omega? It is the velocity in the x-axis, velocity in the y-axis, and angular velocity in the z-axis. Right? All of these three can be independently controlled using three of these wheels. That is the magic of holonomic drive. When you had a differential drive, what did we have? We had a much smaller possibility, just V and omega. It could not slide in the x-axis. It could go forward, it could rotate, but it could not slide like that. But this robot can do it. You can achieve Vx, Vy also, and omega also at the same time. So you could create a spiral like that if you wanted. If you had a pen on the robot, you could create a spiral. You just have to translate while also rotating, which would be impossible for a differential drive to achieve uh, all of these three together. So now the kinematics is actually a mapping between, before I get to that, intuitively you can answer. I think once answering, so anyway, I'll give you the answers, as I said. V2 and V3, if they go like that, then this actually has two components, right? The upward and horizontal components. These two cancel out because they are of the same magnitude, and the robot will move in the vertical direction. This is the y. Uh, if you Okay, there are some interesting situations that can happen. So if you had this combination on the bottom right, if you had one robot pushing like this, one wheel pushing like this, one wheel pushing like this, then you just have to do the vector sum. You do the vector somehow by taking components, for example, and adding all the components in x-axis together and y-axis together. When you do that, you will find that this and this cancels out, and eventually the robot moves in this direction. This, as we discussed, components you take, this and this cancels out, and the robot moves in this direction. Here is an interesting one. If I simply do this, uh, it has, it does move in this direction. That is, and this is all zero, right? So the sum is just this. But we are only discussing V so far, which is basically you can split it again into Vx, Vy. Huh? So if your complete velocity is like that, you can resolve it into Vx, Vy. But we did not discuss omega, which is omega z. That omega is quite curious. Okay, right. Anyway, so there is an omega as well, and the omega will basically make the robot rotate. Oh, I have a lot of things to show. I just realized. Uh, it will rotate about this basically. The robot will go like that. So this is probably more understood when you see it, but I will just 1 second. Give me a second.
स्क्रीन कार्ड मसला है बाबू
Okay, yeah. Sorry, I had to adjust the quiz questions because the amount of topics covered is different from what I had planned. Uh, cool. So now, again, as I said, I am giving away the answers now. So there are three wheel velocities, S1, S2, S3. Remember the matrix, right? You had earlier a relationship between V and omega and VL, VR. Left wheel, right wheel velocities, linear and angular velocity of the entire chassis. This is the chassis velocity, you can call it. And these are wheel velocities. Of course, they are related, right? If you give a certain wheel velocity, it will produce certain chassis velocity. And if you want a certain chassis velocity, there is a corresponding wheel velocity that will achieve that chassis velocity. Uh, I hope that much was clear. So a similar problem is now done in holonomic drive, where we have, okay, I've written just x, y, and omega here, but it actually means Vx, Vy, and omega. So here the question is again the same thing. These S1, S2, S3 is wheel velocities, and these are chassis velocities. Again, which one is easier for the human? Vx, Vy, omega, right? It's easy for me to tell, make the robot go in this direction while also rotating like this. It will achieve that. If I say don't rotate, then it will spin on the spot. If I say go in this direction, it will simply go in that direction. All this, how do I do? This is V. I just resolve it into Vx and Vy. And I say go in this much Vx, this much Vy, and this much angular velocity. That is my commands. This is the high level commands. Or high level is more suitable for humans, right? Controls or high level commands. This is the low level stuff because wheel velocities, especially now, it gets even more complicated. Three wheel velocities that are this and this and this. If I do, it will move like this. That is a very difficult question to answer, right? For simple cases, it's easy. If you have three wheel velocities like that, and if I want to go like this if I give these velocities, which direction will it go? Is a question mark. You can't really tell. That relationship is not so obvious. And if the scale is weird, it's not symmetric, it won't cancel out. So therefore, you need a matrix like the one that is shown here on the right side. If you have this matrix, the job becomes very simple. So this part you pay attention because I have a quiz question also in this part. So uh, what is, if I want to make the robot to go in x-axis, I'll just copy this actually, one second. Mm, huh. So if I want the robot to go in x-axis only, what do I do? What are my wheel velocities? This is my question. What are my wheel velocities if I want the robot to go in x-axis only? It's as simple as doing that. I want it to go in x-axis. I do not want it to move in y-axis. I do not want it to rotate, is what I'm saying. If I do the matrix multiplication, it's just this column here. This all gets cancelled out, right? This all gets cancelled out, and this particular vector comes out. And if you notice, there is a convention that you have to follow as well. So this is the convention that is followed here on the left hand side. You have to define what is positive direction for each wheel. The arrow that I just showed is the positive direction, which means if you get a positive S1 value, you should push the robot, I mean, make the velocity go that way. If you get a negative value, then this way, because positive is not so obvious here, no? For differential drive, it's obvious. Positive is up and negative is down. But this is somewhat circular. So we keep all of them in clockwise direction. This is positive and this is negative, right? So if you notice, what is S1, what is S2, what is S3? It is minus, minus, some minus small value, and plus some double value. So how will I show that? If this is the positive direction, then I'll use a different color and I'll show you the actual velocities. S1 in minus direction, S2 in minus direction, S3 in plus direction, and double, right? That's what it is. So now if you again do the forward kinematics ulta just to understand, did you get the correct answer? Then you will notice that these two are correct answers. This cancels out, I mean, sorry, this cancels out. This and this is equal to this, and you don't get any rotation as well. And you translate equally in this direction. So that is the cheat code that you have. In fact, if you copy this matrix down, you basically have a huge hint for task 2. Uh, this is usually left as an exercise for you to figure out what matrix this is. But anyway, I've given the answer here. So if you do 0, 1, 0, then this is the column that you will get. And you'll get to know that, oh, this velocity, this velocity, this velocity, if you give, it will go in the y-axis, which is basically saying that this should be 0 and third one should be 0, right? Third one should be 0. And first and second should be first positive, negative, second positive. So it pushes like this. Notice this vector. So actually these three columns in the matrix is very interesting. If you give 0.3, 0.3, 0.3, what will happen? It will have only all positive direction, right? All positive direction. This must be very obvious. If you give this, then it's just going to rotate on the spot. It's very important that you visualize all of this. If you did not visualize all the things I'm saying, this would have been a very difficult job to understand what I said. Uh, so let's then, this is the quiz question for your hint, hint. Anyway, you can go, you can give it an attempt. But yeah, this is the basic understanding. If you give 0, 1, 0, 1 0 0 and 0 1 0 0 1, what happens as the output is always an interesting question to ask. You must check if it makes sense. If you want it to go in Vx, what is the number you are getting after the calculation? Substitute those numbers in the actual robot. Put these numbers here and see if it will intuitively make sense. If I want to go in this direction, and if the matrix is giving that the values are this, of course it is wrong. You're saying wheel should go like this, but the chassis should go like this. That is impossible. It's ulta. So probably the matrix is supposed to be all sign change, or maybe this just this column has to become minus, right? Because the omega case is ulta. Instead of going in plus omega, it went in minus omega practically when you checked. So something was wrong in your matrix, which you came up with. Cool. So that is what we are doing. It's a linear transformation from the chassis velocity to the wheel velocities. This is the high level, easy to understand thing. This is the low level, what the robot needs. And this, how to test this is by substituting different kind of standard vectors, 1 0 0, 0 1 0, and 0 0 1 are three things that you must always put and check if it makes sense, because that kind of already says if these three columns make sense. Cool. Yeah, quiz link will be shared very soon. I think I will wrap in 10 minutes. There was this fancy topic of constraints that I will absolutely not touch on today. It's way too much for today's session. So if you are really curious about this, then I would recommend there's one particular lecture series uh, from Northwestern Robotics, uh, and you can search for omni-directional something. If you search that on YouTube, you'll find an excellent series that I have not finished watching. These two videos that I have watched were excellent. So if you oh sorry, Northwestern omnidirectional, if you search, you shall see these part one and part two. I would recommend you to explore this. Probably it's a little advanced. It's like generalizing to any holonomic drive robot. But if you have the patience, you should study this. It's probably not required for the theme, but it is required for your general mental well-being, probably, when you're working in this theme. So, okay then. Again, the team is here and I've finished the presentation. The references I've given. Some papers were of course referred, but it's fine. Now there's one thing that I wanted to show you that I've just worked on last night. Another software that I strongly recommend everyone should explore, which is called Desmos. I have the app here, but you can just go to Google and search Desmos, or just go to desmos.com or something, and you'll see a plotting software. This is the plotting software, Desmos, and it is an excellent tool to test your different understandings of different math concepts and whatnot, especially linear algebra and calculus and all of that. So here what I've done is we discussed a lot about differential drive, right? Uh, so here is my differential drive robot in the bottom left. Uh, the black line, the center of the black line, the green line, the green dot is what I'm moving around. The black line is the differential drive robot. The two black dots that you see here are the wheel positions. That is where the wheel is making contact with the ground. And the two red lines that you see are the left and right wheel velocities. So if I increase the linear velocity, then of course the red line should increase. If I decrease it and make it negative, of course so here on the top left, observe, I can't really point, but on the top left over here, there are two sliders, V and omega. So V and omega are the high level commands. I want it to go linearly at this velocity, and I want to steer at this velocity. So that is what is being shown here. If I steer to the right and with the small velocity with high angular small angular velocity, then the circle that it will trace is shown here. In fact, this is probably an interesting situation where the arrows are ulta and all of that, but I might need to check the um, exactness of this, but intuitively this is what it is. You can see the V and omega. In fact, you can see the R, and you can see the VLVR in the red line. But in fact, the linear algebra, if you have studied linear algebra, you would have seen, uh, I would strongly recommend one more recommendation, 3 blue, 1 brown linear algebra series. He will show you an animation that I'm showing here for a different kind of system. But what I have here is left wheel and right wheel velocities in the red dot and V and omega in the green dot. So if I give a very, if I give only linear velocity, so it's if I steer to the left, it will turn left. If I steer to the right, it will turn right. If I give only linear velocity, then it will go straight. And the red dot clearly shows equal magnitude for both left and right. So there are two different graph plots with two different axes shown overlapped on top of each other. One of the graph is V and omega, which is the green dot graph, and the VLVR is the other graph. So there are two different graphs laid on top of each other. And what is happening is that matrix that we discussed earlier, a 2 by 2 matrix, that is doing the transformation from the green dot to the red dot. So you can, if you're curious, you should study this and understand this in a deeper level. So that is Desmos for you, and I would recommend you explore Desmos as well. So the key takeaways is, of course, all the technical stuff that we discussed. But apart from that, in general, linear algebra from 3 blue, 1 brown, I have suggested you should explore if you have not already. Uh, and if you want advanced stuff, then I have already suggested this particular Northwestern University course. So that's fine. Desmos was the other thing that I suggested. Desmos for plotting, visualization. Because I personally prefer visual learning. Maybe if you're not, then you don't care about Desmos. But if you are, then I would recommend Desmos. Cool. I think that is a wrap for today's sessions. Any questions you guys have, you can ask. Else, we will be closing the stream and sharing the quiz link and a lot of things. So, um, yeah, questions quickly, if any questions. Yeah, link will be shared in the deck soon. Uh, okay, this is the last part where we wait for the questions. If there are none, then we'll be ending stream as well. Uh, Thank you all for coming. And I mean, at least for the YouTube people, WebEx people will stay here. There are some things to be done. Uh, but for the YouTube people, I think the session will be ending soon. So if you have any questions, you can ask your questions. Else, that's all for today. Thanks for coming, and make sure you check eYRC website if you have not already and register and all of that. Um, WebEx people, of course, stay online. We have some things to be done before we wrap.